6.3, we will be simplifying our radical expressions. So in order to simplify, we need to know a property and then the definition of simplification. So a property that we need to know is that we can work this equation sign both ways. If we have two things inside that are multiplied together, we can split them up. Sometimes we'll be able to take the square root of one of them, and that will get us to simplify. The other way, we can take two things with the same index, either a square root or a cube root, and we can combine whatever's inside by multiplying them together. So remember, equal signs work both ways. Doesn't mean that we can't just combine. We can also uncombine. So, simplified form. How do we know when we're done with these next couple of problems? So to have a fraction that is simplified, it needs to meet all three of these conditions. So condition number 1 says that the radicand has no factor raised to a power greater than or equal to the index. So this very first one, we have the cube root of x to the 5th. Because this 5 is bigger than this 3, that is not okay. There's still some simplifying that needs to happen. The next condition is that the radicand does not contain a fraction. So if you have a fraction underneath your square root, cube root, whatever root you have, you need to do more. And then the third condition is the weirdest one. You cannot have a radical in the denominator of your fraction. So not only can you not have fractions underneath the square root, if you have a fraction, the stuff on the bottom cannot have a radical. So let's see how we can fix all of these mistakes and get them in their simplified form. So the very first problem, problem 9, is the square root of x to the 5th power. So again, if they don't tell you what the index is, we always assume that it's 2. So that means that we can simplify. X to the 5th is really x times x times x times x times x. So if it's a square root, that means we need groups of 2 before we can leave the square root. So let's see how many groups of 2 we can make. There's one that we can take out, and then there's another one that we can take out. And this final x doesn't have anybody to partner up with, so he has to stay inside of the square root. So we pulled out x squared, or 2 groups of x's, and then there's one guy left over. So there's our answer. We have our exponent smaller than our index. There's no fractions involved anywhere. So let's do the same thing for number 11. Hopefully you've noticed that there's an easier way to do this. If that's the cube root of q to the 7, instead of writing out 7 q's and seeing how many groups we can make, think about what we did. How many times can 3 fit into 7? It fits in, we don't need that, it fits in twice. So we have q squared that we can take out, or 2 groups of 3 q's, and then there's one left over. So he needs to go inside the house still. Let's do that with more than one variable for number 13. The square root of a to the 5th, b to the 4th. So how many groups of 2 can we make out of 5 a's? 2 goes into 5 twice, and then there's one left over. A squared root a. And then we do the same thing for the b's. How many times can 2 go into 4? Twice, and it goes in evenly. So we are totally done. There's no b's left inside of our square root. Last one like this, and this one's a little harder just because it has that negative out front. But all that means is I have negative 1 times the 4th root of x to the 8th, y to the 13th. Everything else is exactly the same. So we have this negative 1 floating on the outside. And then how many groups of 4 can we make out of 8 x's? Well, we can make exactly 2. And then how many times can 4 go into 13? It goes in 3 times, which gives us 12. So that means that there's one y that has to stay inside. Double check. This is y to the 1st power. We have the 4th root. So we can't make any more groups. So that means we're done. Not too bad. So let's do some with numbers. Sometimes numbers are actually harder than the exponents just because when you have x to the fifth, you know exactly how many x's you have. X times x times x. When I give you 28, you might not exactly know what factors you have. So in order to find out what we can take out of here, we need to split this up into its factors. We don't want to type that into our calculator anymore and get a messy decimal. We want an exact answer. So let's break up 28. We can do anything that comes to mind. How about 2 and 14? And then 2 can't be simplified anymore, but 14 can, and that breaks down to 2 and 7. So I can just as easily write the square root of 28 as the square root of 2 times 2 times 7. And now it's really easy to see that I have a group of 2 2's. So that means I can take some 2's out, and 7 doesn't have any friends, so he has to stay inside. And these two answers are exactly the same thing, the square root of 28 and 2 root 7. When you type them both in your calculator, you get a messy decimal, but 2 root 7 is exact. Number 19, kind of the same deal, except there's a 5 on the outside. So remember, that just means that we're going to take 5 and multiply it by whatever we break up this negative 18 to, or the square root of 18 to. So let's break this down into whatever comes to mind first. How about 9 and 2? And then 9 can be broken up into 3 and 3. So I could write this as 5 times the square root of 3 times 2. And because it's a square root, we need groups of 2 again, so 3 can leave. And we are going to multiply 5 and 3 together. So we end up with 15 times the square root of 2, or 15 root 2. Hopefully you've kind of noticed a pattern here. Instead of breaking it up every time, you could think about perfect squares that go into your numbers. So with 28, what's a perfect square that goes into it? Well, 4. So we could have said it's the square root of 4 times the square root of 7, and we would have gotten 2 root 7. For 18, we could have broken that up into 5 times the square root of 9. That's a perfect square, times the square root of 2. And then we see we'd get 5 times 3 again, root 2. You can always make the factor tree if you forget that, especially for one like 21, the next one that we have to do here. It's a cube root. So knowing our perfect cubes is always a little harder than our perfect squares. So let's just split 54 up. If I want to split this up, anything that comes to mind, let's do 6 and 9. And then break these guys up. 2 and 3, 3 and 3, and then they can't be broken up anymore. So I have the cube root of 2 times 3 times 3 times 3. And then we can take out one group of 3's. So we end up with 3 times the cube root of 2. If you did notice that you had a perfect cube in there, 27, the cube root of 27 is 3. You could have done that as well. So now the next one, we have numbers and letters. Combine the last two slides together. So it's a square root. If you want, you can write everything out. 25 can be broken up into 5 times 5 times A times B times B times B. So see what you can make groups of. So we can take out a group of 5. We can take out a group of B. 1A and 1B are left in there. So on the outside, we have 5B times the square root of AB. And you could also do that the shorthand way. Hopefully everyone knows the square root of 25 is 5. Can't take out any A's, but you can take out one group of B, and 1 would be left inside. Let's throw some fractions in there. So for 29, the first one that we see here, remember in our simplification rules, how we know when we're done way back here? You cannot have fractions anywhere. This condition right here. The Radicand does not contain a fraction. So what we want to do first to fix that is see if we can simplify what's on the inside. So if we look at this first problem, I have x cubed divided by x. If you remember your exponent rules, we can just subtract those exponents, and we are left with the square root of x squared. And that means we get exactly x. Starts off with a fraction, but we get a nice simple x when we're done. The next one, same thing, 98 over 2. See if you can simplify before we have to take care of any radicals in the denominator. So 98 divided by 2 simplifies to exactly 49. 49 is one of our perfect squares. It's just 7. If you type stuff like that into your calculator, you will get 7 out, but obviously we can't type one like 29 in our calculators. So let's do the same thing for 35. We are taking the cube root of 3 divided by 24. So let's see if we can simplify what's on the inside. 3/24 simplifies to 1/8. We still have a fraction in there. So we can't do what we did for the last two problems. We need to split this up into the cube root of 1, what's on top, divided by the cube root of 8, what's on the bottom. And now these are perfect squares that we can simplify. The cube root of 1 is just 1, and the cube root of 8 is 2. 1/2 is perfectly acceptable. We can have a fraction in our answer as long as there is no radical involved. Very last problem for this section. We have 7 times the square root of 18, all divided by 9. Remember, when the numbers are just sitting next to each other, they are multiplying. So be very careful that you don't want to simplify this 18 divided by 9 and get the square root of 2. 18 is inside the square root and 9 is not. That means that they cannot hang out. So we need to see if we can simplify what's inside of the square root. We've already done the square root of 18. And if you don't remember, let's just think about it. What's a perfect square that goes into 18? Well, 9 goes into it. So we can split this up into the square root of 9 times the square root of 2, all divided by 9. So the square root of 9 is 3. So we'll get 7 times 3, or 21, root 2, all divided by 9. We can't simplify our radical anymore, that square root of 2, but we have numbers on the outside that can be simplified. 21 divided by 9 can be reduced, not to a nice pretty number, still a fraction, but 3 goes into both of them. So 21 divided by 3 will give us 7. Can't forget that root 2. And in the denominator we end up with 3. And that is it for section 6.3.